Hello, and welcome to a 10-minute tutorial on the Hopcroft Karp algorithm. We are going to cover the following things in this tutorial. Firstly, we will see the problem that the algorithm helps us in solving. Then, we will discuss some keywords and terms we need to understand before studying the algorithm. In the third part, we will look at the algorithm itself and see how it works. This will be followed by a short case study where we will run through an example problem. And in the final section, we will discuss the time complexity of the algorithm. The problem under consideration is the maximum bipartite matching problem. Consider a situation where there are m job applicants and n jobs are available. Each applicant has a subset of jobs he or she is interested in. Each job opening can only accept one applicant, and a job applicant can only be appointed for one job. We need to find an assignment of jobs to applicants in such a way that as many applicants as possible get jobs. We can model such problems using a bipartite graph. As you can see, this is a bipartite graph over here. And Hopcroft Karp algorithm can help us find solution to such problems. But before we go any further, we need to discuss a few terms first. Firstly, what is a bipartite graph? A graph is said to be bipartite if its vertices can be divided into two independent sets, x and y, in such a manner that every edge in E either connects a vertex from x to y or y to x. Now, consider this example given here. We can see that graph A is bipartite, while graph B is not bipartite, and that's because graph B contains an edge between vertices of the same set. Now that we know what a bipartite graph is, let's see what does a matching imply. A matching M is a subset of the edges of our graph such that for every vertex in our graph, at most one edge in M can be incident on any vertex V. For example, this graph over here is not a matching because two edges in the matching map to this same vertex, which cannot happen. A maximum matching is a matching which contains the maximum edges possible. Coming to the concept of alternating and augmenting paths. An alternating path is a path in which edges belong alternately to the matching and non-matching set. An augmenting path is a special alternating path in which the starting and ending vertex is always a free vertex. In the example shown here, the path x1, y2, x4 and y4 is an alternating path, while the path x3, y2, x1 and y3 is an augmenting path since it starts at x3 and ends at y3, both of which are free vertices. Symmetric difference of two sets A and B is a set which contains only those elements of A and B which are not common to them. Also, for the algorithm, we would need to find the maximal set of vertex disjoint minimum length augmenting paths, which is the set S. So let's see what does it mean. Firstly, it is a set of augmenting paths. Second, no two paths in S share the same vertex, which means that it is vertex disjoint. And finally, if the length of the smallest augmenting path is k, then all paths in S should be of length k. Let's look at the algorithm now. Here's the pseudocode. First, we initialize M to the empty set since we don't have any matchings at the moment. Then, as long as there is an augmenting path in our graph, we execute the while loop. For each iteration, we find the maximal set of vertex disjoint minimum length augmenting paths. In order to do this, we use breadth first search to generate the layered graph and then find all the augmenting paths using depth first search. Then we take the symmetric difference of M and P. Finally, once all the iterations are over, we return the matching set M, which will be the maximum matching set.
We will now go through an example. 6 people try to find jobs. They select jobs out of the 6 available ones based on what they would like to do, without having any particular preferences. Using the given table, we can model the problem as a bipartite graph, so we can now run the Hopcroft Karp algorithm. We initialize M to be empty. Then we try to find an augmenting path by running BFS from all the free vertices from the left side. The first iteration is simple. As all the vertices are free, BFS will output the same graph, so in this iteration we will skip straight to DFS. We choose a free vertex from the right set, in this case 1, and we use depth first search to find another free vertex on the left hand side. Because we are looking for vertex disjoint sets, we delete the selected nodes and all their edges, and we keep track of the path that we used. Here E gets orphaned, and there is no way to reach the vertex this iteration, so we delete it. We do the same process of running DFS and removing vertices for all the remaining free vertices in the right set. Now we calculate the symmetric difference. As M is empty, all the paths are added. We will show now how BFS constructs the alternate level graph. As before, we run BFS picking a free vertex from the left set, in this case E. We try to link it with a free vertex from the other set using alternate edges. So, E is connected to 1 through an unmarked edge. 1 is connected to J through a marked edge. J is connected to 2 and 4. 2 is connected to O and 4 to Z. And finally Z is connected to 5 and 6. We can now stop because we found a free vertex. We now pick another free vertex, N. After running BFS on N, we end up with this graph. After this, DFS will be executed from either 5 or 6. Now we start running DFS on the free vertices from the right set. Also, when running DFS, you can see that there are multiple paths that can be chosen. So, while the algorithm finds a maximum matching, it doesn't mean it's a unique one. We just found a free vertex, so we stop and delete all the nodes because we are looking for disjoint set vertices. In the process of deleting the path, 6 gets orphaned and we are left with no free vertices to run DFS, so the iteration ends. We now go back to doing the symmetrical difference. We remove the edge Z4 because it is in both sets and we add N4 and Z5 to the matching. We go back to the top trying to find an augmenting path, so we run BFS from the only free vertex left, E. It is important to observe that after each iteration, the length of the augmenting path increases. Now, by running DFS on 6, we get this path connecting it to E. Now we will compute the symmetrical difference to augment M. And now there are no more free vertices, thus the maximum matching has been found. Time complexity. M is initialized in constant time. The while loop will run for at most 2 square root of v times. Well, as you could have observed, the length of each augmenting path found increases by at least 1 after each iteration. Assume we have a maximum matching M star and a matching M after square root of v initial iterations. Using the lemma from point 3, for which you can find the proof in the video's description, we can figure out that after the initial square root of v iterations, there will be at most another square root of v iterations. So, in total, the while loop will run for almost 2 times square root of v times, which is big O of square root of v. Breadth first search and depth first search take big O of v time assuming the graph is connected. If it contains isolated vertices, we can simply remove them before executing the algorithm without modifying the complexity or the results. To obtain the symmetrical difference, it will take at most big O of v time. M can be returned in constant time. Thus, the overall time of the algorithm is big O of E times square root of v.
We have finally come to the end of this tutorial. To summarize, we saw how the Hopcroft Karp algorithm, an iterative algorithm, can help us find the maximum matching in a bipartite graph. We also went through an example and saw why this algorithm runs in big omega of mod e times square root of v. You can learn more about this algorithm by following the references given in the description below. Thank you for watching, and we hope you found this useful.